Okay, this is a video about simple AC circuit analysis. So here's the circuit, and we're going to find V2, V3, and V1, and then we'll also find the current running through each component on the circuit. Okay. I'll leave that there. Now, let's start by, we need to combine these two impedances. So we're going to do that first. So I'll write impedance, and they're in parallel. So I'll put impedance parallel equals R multiplied by J omega L. Alright, where omega is equal to 2 pi times the frequency, and J is our imaginary number. Okay, that was really badly written, but J is the imaginary number. Okay, back to this. R times J omega L, and where L is the inductance, or the value of the inductor. And then R plus J omega L. So we can put the values in. 400 times J times 2 pi times, now for this question, F is 50 hertz times 220, and it's millihertz, millihenries rather, the inductor value. Just move that back in. The inductor value is millihenries, so to the negative 3. And then 400 plus the same thing. Okay, now we're going to put this in a calculator. Now, the imaginary number, I'm going to use this calculator. It's the Casio FX100 AU, and it has an imaginary number built in. So you can just click the imaginary number and it gives you the I. You don't have to mess around or do anything else. So I'll be doing it quickly, but if you don't have this calculator, you'll have to do more working, but that is unfortunate indeed. So we put 400 times J omega L. Have this so you can see it. So 220. That's the inductor value. And then this 400 plus J omega, that's omega, and then L. We get an impedance of this 11.596 plus 67.111 J. So that's our impedance in this part of the circuit. So I've now combined those bits. I'm now going to do a voltage divider to find the voltage drop across through these two combined wires now. So the voltage divider is, and V2 and V3 are equal to each other. So we can say that V2 equals V3, which equals the 240 voltage source multiplied by the impedance of this, which is 11.596 plus 67.111 J, and that's over the impedance of the capacitor, which is here, plus the parallel impedance of the resistor and an inductor. So impedance of a capacitor is 1 over J omega C, 15 by 10 to the negative 6, and that's plus this. Okay, now this is going to get very messy in the calculator, so we can take it in steps. I'll multiply the top first. And we get this 2,783.04 plus 16,106.64J, and that's over all of that, which I'll now do. So 1 over J omega C plus impedance, parallel impedance, gives us this. Okay, now I'm just going to divide those to get out a number. Okay, equals, so it equals that, minus 108.77 plus 27.87J. Now the beauty of this calculator, you can convert straight into exponential form, or exponential format. So if you have this calculator, so you do it, God, how do you go back without deleting everything? Okay, they're good. Got our number there, you go shift, then you click complex 2, it says complex, and then we want that form, exponential form, and that is assigned to button 3, equals. We get out a number, 112.294 e to the j 2.89 volts. Okay, that equals V2, which equals V3. Now to find the voltage through V1, which is through the capacitor here, we're going to do, just going to write a little equation. V source equals V1 plus V2, V3, because they're the same, right? So we have 240. 240 minus the V2, V3, which is 112.294 e to the j 2.89, and that equals V1. Now, this has no phase, so we can just write, so we can just do 240, we'll just put this in anyway, it's not necessary because it has no phase. So 240, e to the j is 0, right? And then minus 112.294 e to the j 2.89. What do we get? We get, oh, that's in polar form. Oh, I don't know what form it's called. I always go to exponential form, so straight to exponential. We get V1 is 349.87 e to the j negative 0.079. Now, we've solved those voltages. Now we can just solve for the current. So we can solve for the current now in our branches by using V equals IR. So we'll solve current 1. So 349.87 e to the j 0.079 over the impedance R, impedance Z. We'll use V equals IZ. So this is the impedance, J 2 pi. So this is what we did before up the top. So you just have to write it all again. So I1 equals, okay, so after putting it in the calculator, I1 equals 1.648 e to the j 1.49 amps. Now, do the same. We'll do the resistor, that's a bit easier. It's just 112.294 e to the j 2.89 over 400, which is I2. Alright, and that equals 0.280 e to the j 2.89. And finally the inductor. So it's the same voltage as the resistor. And the impedance, J omega L. Alright, and that comes out to 1.624 e to the j 1.31 amps.